Deep learning is a subfield of machine learning that focuses on training large neural networks with many layers to automatically learn hierarchical representations from data. To understand why deep learning became so important, it helps to recall the earlier paradigm of feature engineering. In traditional machine learning pipelines, practitioners spent most of their effort manually designing features that would expose useful structure in the data. Deep learning shifted the burden of representation design from humans to optimization. Instead of handcrafting features, we define a parameterized function with many layers and let gradient-based learning discover useful intermediate representations. At its core, deep learning is about function approximation under very high-dimensional parameter spaces. A deep neural network is simply a composition of many nonlinear transformations. Each layer takes a vector as input, applies an affine transformation followed by a nonlinear activation, and passes the result to the next layer. While this sounds simple, the power emerges from depth. Stacking layers allows the network to build increasingly abstract representations. Early layers might detect edges in images or local token patterns in text. Later layers combine these primitives into higher-level concepts such as object parts, semantic roles, or discourse-level relationships. One of the key theoretical motivations behind deep learning is the notion of hierarchical feature learning. Many real-world signals are generated by hierarchical processes. Images are composed of pixels that form edges, edges form textures, textures form object parts, and parts form objects. Language similarly exhibits hierarchical structure from characters to morphemes to words to phrases to full semantic meaning. Deep architectures naturally mirror this compositional structure, allowing them to model complex distributions more efficiently than shallow models that would require exponentially many units to represent the same functions. The basic building block of deep learning systems is the artificial neuron, though in modern practice it is better understood as a simple nonlinear unit. Mathematically, a neuron computes a weighted sum of its inputs, adds a bias term, and applies a nonlinear activation function. Common activation functions include ReLU, GeLU, sigmoid, and tanh. The nonlinearity is essential. Without it, stacking layers would collapse into a single linear transformation regardless of depth. The presence of nonlinearities allows the network to approximate highly complex functions. Training deep networks involves defining an objective function that measures the discrepancy between the model's predictions and the desired outputs. This objective is often called the loss function. The parameters of the network are optimized using gradient-based methods, most commonly stochastic gradient descent, and its adaptive variants. The gradients are computed efficiently using backpropagation, which applies the chain rule of calculus through the computational graph. One reason deep learning became practical only in the last decade is the convergence of three enabling factors. The first is data availability. Deep networks have very high capacity and require large datasets to generalize well. The explosion of digital data from the web, sensors, and user interactions provided the necessary scale. The second factor is computational power, particularly GPUs and later specialized accelerators such as TPUs. Matrix multiplications, which dominate neural network computation, map extremely well to parallel hardware. The third factor is algorithmic improvements, including better initialization schemes, improved activation functions like ReLU that mitigate vanishing gradients, normalization techniques such as batch normalization and layer normalization, and more robust optimization algorithms. A central concept in deep learning is representation learning. Rather than learning a direct mapping from input to output only, the network learns intermediate representations that capture salient structure in the data. These representations often transfer across tasks. For example, a convolutional network trained on large-scale image classification learns visual features that can be reused for detection, segmentation, or even unrelated vision tasks. Similarly, large language models learn token embeddings and contextual representations that can be fine-tuned for many downstream NLP problems. Depth brings expressive power but also introduces optimization challenges. One classic issue is the vanishing and exploding gradient problem. When gradients are propagated backward through many layers, repeated multiplication by weights and activation derivatives can cause gradients to shrink toward zero or grow uncontrollably. This makes early layers difficult to train. Architectural innovations such as residual connections, gating mechanisms in recurrent networks, and normalization layers were developed partly to address this issue. Regularization plays a crucial role in deep learning because these models often contain millions or billions of parameters. Without constraints, they can easily memorize the training data. Techniques such as dropout, weight decay, data augmentation, and early stopping help improve generalization. Interestingly, modern deep learning sometimes operates in a regime where models are massively over-parameterized yet still generalize well, a phenomenon that has motivated new theoretical research into implicit regularization and the geometry of optimization landscapes. Different domains have given rise to specialized deep learning architectures. In computer vision, convolutional neural networks exploit spatial locality and translation invariance. Convolutions share weights across spatial locations, dramatically reducing parameter count and improving sample efficiency. Pooling layers provide a form of downsampling and invariance. Over time, architectures evolved from early models to very deep residual networks and vision transformers that incorporate attention mechanisms. In natural language processing, the field moved from recurrent neural networks and LSTMs toward attention-based transformer architectures. Transformers rely heavily on self-attention, which allows each token to directly attend to all other tokens in the sequence. This provides better modeling of long-range dependencies and enables massive parallelization during training.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.